Welcome back to Two Men, One Course podcast. My name is Pete. I'm your host. Tyler and I are happy to see you here. We are hoping that you have an amazing day. Okay. And before we get into the detail, always, so let's start with a dad joke. So, are you guys ready? Okay. The question is, why couldn't a green pepper practice archery? Why couldn't a green pepper practice archery? Well, because he doesn't have an arrow. Well, anyway, so all right, so this lab that you're gonna do next week, I think it's the first time you're doing acid-base chemistry, okay? And before we get into the detail here, this is the background, the concept that you need to know. From the lecture, you should know that in solution, the acidic species is called either proton or hydronium ion. They are the same thing, essentially the same thing, okay? And we have in 1909, way long back there, before Snapchat was invented, long back there, Sorensen, she was a Danish chemist and very famous for doing like pH, acid-base chemistry, acidity, alkalinity. Anyway, okay, he proposed a more practical way to measure acidity in solution. Okay, now let's talk about let's take a look at all the substance we have right here. We have water, wine, ammonia solution, cleaning solution, and milk. Okay, so all these, they have different acidity in them, right, in the solution. But how do you measure them? Well, Sorensen came up with an easy scale. All right, we're going to talk about this scale just a little bit. But now let's talk about this real quick. What makes a solution acidic? Or water, just look at water. What makes a water acidic? What's in there that make water acidic? Well, I mentioned before, a species that is considered acidic in solution is called either proton or hydronium ion. Okay, so all of them have some amount of hydronium ion, maybe high or small, depends on the solution. But in water, the amount or the concentration of hydronium ion is 10 to the negative 7 molar. It's really, really small. Okay, we call water neutral, right? In ammonia solution, the cleaning solution, we all know, most of us know this is basic solution. The amount of proton is going to be even less. How much less? 10 to the negative 7, 10 to the negative 12. That's about 10,000 times less amount of proton or hydronium ion in this solution compared to water. Okay, wine is a little more acidic than water, so the concentration is 10 to the negative 4th molar, about 1,000 times. All right, and milk is relatively neutral, a little bit more acidic than water, just slightly. All right, but now here's a problem though. Use this number. We had to get that the amount of the concentration of hydronium ion tells you how acidic a solution is. But if you look at this number is really complicated. It's just too long. All right, so Sorensen came in and proposed an easier way, a more practical way to represent acidity in water, right? Sorry, in solution, and he came up with a pH scale. Okay, now let's talk about pH real quick. So the pH is defined as negative log of the concentration of acidic species, either proton or hydronium ion. They're the same thing. Okay, so basically now water, right? You guys know water pH 7, right? But how do you get to there? Well, so just plug in this a map right here. The concentration of hydronium ion in water is 10 to negative 7. Plug in there. pH is equal to negative log of the concentration of hydronium ion, right? And if you do calculation right here, you should get 7 right there. All right, so water, I put in 7 right there. All right, before we go further, so can you pause the video, calculate the pH of each solution, ammonia, wine, and then milk. All right. All right, so on the right side right here, so ammonia, so the concentration of proton is 4 times 10 to the negative 12 molar. Like that. All right. So in your calculator, so watch out. A lot of students make this mistake. In your calculator, you should type negative log and parentheses. 4 times 10 to the negative 12 and parentheses. If you don't have parentheses, the log going to be applied only to 4, not 10 to the negative 12, and you get a weird number. Okay, the pH number should be easy number. This one is 11.4. Okay, Now down here, wine, negative log of 3.2 times 10 to the negative fourth, you should get 3.5. Now a little bit more, that's quite a lot more acidic than water. Okay, and one more. So milk, negative log of 3.2 times 10 to the negative 7, 6.5, slightly more acidic than water. Okay, all right, that's about the pH. Okay, now here's how we measure pH in the lab. All right, you can use a pH paper. You might be more familiar with litmus paper, right? But we also have pH paper. You could also use an indicator, and you're going to be using the phenolphthalein either this lab or the next lab. So I don't remember, but yeah, phenolphthalein, you'll be using it. We also have a universal indicator that change color. I go back here. Universal indicator change color as pH changes. It's pretty colorful. And this is a colorful lab. So other types of indicator we have, so universal indicator, phenolphthalein, methyl orange, thymol blue, bromo thymol blue, phenol red, quite a lot of it. It change color. All right. Anything that that is colorful in nature, for example, the red cabbage pH indicator. So the color of red cabbage change as pH changes, similar to the universal indicator, but the color changes differently. And anything that's colorful in nature, those could be an indicator. All right. Another type of the way that we measure pH is we can use a pH meter. Right, just so we have the look like a meter right here. We got a probe that dip into the solution, and you just read the pH on it. But this the pH meter needs to be calibrated first. Okay. All right, let's do one practice together. So the let's read it real quick. The concentration of proton ion in the bottom of table wine was 3.2 times 10 negative 4 molar right after the cork was removed. Only half of the wine was consumed. Okay. The other half, after it had been standing open to the air for a month, whoa, live away for a month, okay, was found to have a hydrogen ion concentration equal to 10 to negative third molar, so a little bit more acidic there, okay. Calculate the pH of the wine in 2 occasions. Okay, the first occasion, so when you open it, drink right then, the pH of that wine is 3.2 times 10 negative 4th molar. Leave it for a month, it becomes more acidic. Calculate the pH. Start from the left side. All right. So pH is equal to negative log of 3.2 times 10 negative 4th molar. Ta-da, 3.5. On the right side, so negative log of 10 to negative third, 3. Okay. So what actually really happened? So I'll talk about the chemistry in life a little. When you open a bottle of wine, beer, anything that have alcohol or ethanol in it. So the oxygen in the air will get in there and oxidize the ethanol. Yeah, we have sunlight to just like supply power, supply the energy for this reaction. And the ethanol look like that, get oxidized to acetic acid. Do you guys know what acetic acid is? You will see this acetic acid pretty often if you take Gen Chem lab, no, Gen Chem 2, OChem 1, and OChem 2. You'll see this guy pretty often. So acetic acid is actually vinegar. Okay, but the vinegar is dilute acetic acid, so we can consume it. All right. Now talk about the alcohol and detoxification real quick. Okay, do you guys drink alcohol? You probably think, oh, I'm 18, 19, no, I can't drink alcohol. No, I'm not asking about your age. Do you drink alcohol? Oh, come on, don't be naive. So, well, if you want to drink alcohol, I know you can find a way. So, right. Now, alcohol and detoxification. So alcohol, if you drink a lot of alcohol, well, you get to the stage that have way too much ethanol level in your blood. And we call that stage drunk, right? You're drunk, man. And ethanol is actually toxic to your body. So our body have to detoxify it, so get rid of it, all right? So okay, the better word is excretion, okay? And that happened in the liver. Start with the liver. Just start it right here. It can happen anywhere, but start at the liver. So ethanol will, when you drink ethanol, it goes to your blood. The blood take ethanol to your liver, and in your liver there are quite a lot of enzymes. Okay, a couple of them that involved in this process is we have alcohol dehydrogenase, convert alcohol to acetaldehyde, and then the aldehyde dehydrogenase convert aldehyde to acetic acid, just like what we saw earlier, same oxidation reaction. All right, and the good thing about converting ethanol to acetic acid is acetic acid have more oxygen. This guy is more polar and soluble in water better. All right. The good thing of we have everything dissolved in water better because all metabolism in our body occur in water, and that's the reason why our body, was it 3/4 of our body is water. Okay. And much more soluble in water. We can take acetic acid to a Krebs cycle, making ATP, fatty acid, and convert all carbons and oxygen and hydrogen to carbon dioxide and gas, and water. So water you pee out, carbon dioxide you inhale, exhale. Okay, so everything that you take get converted to carbon dioxide and water. All right, and that's the reason why if you drink a lot of alcohol, you gain weight because it produces ATP and fatty acid. To make yourself sober, so if you get you have hangover, so people say you drink a lot of water. Well, the reason is when you drink a lot of water, you pee more often, you just increase the rate of excretion. All right. Okay, all right, now we have learned about pH. Now go a little bit to pOH. So basically, pOH is a pH, but in a reverse pH scale. All right, but not many people use it anymore. So because we have a pH scale, but I want to show you the relationship between pH and pOH. Okay, I don't know if you have seen the dissociation constant of water yet, but I just want to show you. So Kw, that's a dissociation constant of water, which is the concentration of hydronium ion times concentration of hydroxide ion in the solution is equal to 10⁻14. Really, really small. Okay, really small. But take a look at the math real quick. So I'm going to take negative log on both sides. Okay, take negative log on both sides. And a property of log, so I'm sure you have seen this in high school. Negative log can distribute to the term inside the log. I'll take a look real quick. So it's super simple here. If you haven't seen it, this is really simple. Take negative log, go distribute into this term inside. You're going to have negative log of proton, negative log of concentration of hydroxide ion. Just distribute inside, right? Spread it out. Same thing on the right side. So we have negative log of this term. You can do negative log of 1 and negative log of 10⁻14, like that. Here's the thing though. Negative log of 1 base log base 10 is 0. This term is 0, right? And another property of log, you can take the exponent, put it right in front of log, just like that. So we can take -14 right in front of it. You get that. And log of 10, base 10 is 1. Super simple there. Negative and negative, you get positive. So on the right side, it's just 14. You know? Now, on the left side, though, it's very simple. Negative log of proton, of concentration of proton. Have you seen this before? That is the definition of a pH. Really simple. Yeah? And negative log of concentration of hydroxide ion, that's the definition of pOH right here. All right? Basically, what I want to say is pH plus pOH is 14. Well, that's the relationship. Basically, what I want to show you, you can convert the concentration of proton to the concentration of hydroxide ion, convert to pOH, convert to pH, right? With all this relationship. Start from proton to hydroxide ion. Well, the product of concentration of proton times concentration of hydroxide ion is Kw, 10 to -14. Right? You can convert this guy back and forth. All right, so Kw is 10 to -14. You can convert pH and the concentration of hydronium ion or proton by using the definition of pH. Okay, and the same thing on the hydroxide side, same thing. That's the definition of OH, pOH. I mean, and pH and pOH can be converted to one another because combine them is equal to 14. All right, let's do one example together. So you have to do it on your own for the pre-lab quiz. So let's do this together real quick. In a sodium hydroxide solution, the concentration of OH is that number. Calculate the pH of the solution. Okay. Normally, if I have the concentration of OH, I usually go to concentration of proton and then convert it to the pH. But for the sake of practicing, I'm going to go the other way. So OH go to the pOH and then go to the pH. Okay, so I'm going this route. All right, so convert concentration of hydroxide ion to the POH first. Here we go. Plug in 2.9 times 10 negative fourth right here. All right, negative log. Don't forget the parenthesis in the 2.9 times 10 negative fourth and then parenthesis. All right, you should get about 3.5376. Keep that. Don't round them off yet. Just keep it like that. And then now we have a POH now. Convert it to the pH using this relationship. All right, pH plus POH is 14. We want to know pH, so I'm going to move POH to the right side and then plug that in. So you get about 10.463, and that is about 10. Okay. All right, that's about acid-base chemistry. All right, before one more concept that you need to know: dilution, because you have to do some dilution. All right. Now let's take a look right here. So if I have a cup of coffee and really concentrated caffeine in it, really concentrated, let's say 10 molar. All right. I'm not sure how much you know about molarity, but molarity is a unit of concentration divided by number of moles per liter volume. All right, per volume. Okay, so 10 molar is pretty concentrated. And real caffeine is not really 10 molar. No, it's no. But I just make up the number. Let's say we have 10 molar caffeine in this cup. So if I have a syringe, take a 1 milliliter of this solution, just 1 milliliter. What is the concentration of that caffeine in the syringe? Well, I'll ask you this. If you take a sip on this caffeine and you take a sip if you take a sip of this coffee in the cup and take a sip of the coffee in the syringe, do they taste the same? Well, it's supposed to taste the same. It's just the same thing. We just take 1 milliliter out of it, right? So the concentration have to be the same. Okay, so 10 molar here, you take 1 milliliter. That 1 milliliter is gonna be 10 molar. Now, what's the mole though? Can you calculate moles of the caffeine in the syringe? Sure, you do. Look at right here. Go back to this equation. So moles equal to M times V on both sides. You can calculate for moles. All right. So the molarity is 10 molar. V is in liter, but right now we have 1 milliliter, which is 1 over 1,000. We have divided by 1,000. All right. So the mole should be 0.0100 mole. That's a mole of caffeine in this syringe, just in this syringe. Okay. All right. I'm going to transfer the coffee in the syringe, this 1 milliliter, to a test tube. Okay. I put in a test tube. What is the concentration of caffeine in this test tube though? Do you know? Do they taste the same though? Well, it's gonna be the same from the cup, from the syringe, from the test tube. They are all the same thing from the same coffee in the cup. They have to taste the same. So the concentration stay the same. Nothing changed. What about mole though? Well, this caffeine in here come from the syringe. Mole has to be the same. All right, nothing changed yet. All right, now the dilution is right here. So watch. I'm going to add 1 milliliter of water to this test tube. Are you ready? All right, 1, 2, 3, add. So you end up with 2 milliliter solution. All right, 2 milliliter solution. What is the concentration of caffeine? You should get a feeling, so it's going to be a little bit dilute, right? We'll be dilute by half, right? Start with 1 milliliter, add up to 2 milliliter. So the concentration should go down by half as well. So 5 molar, right? And what about the mole though? How much in mole of caffeine are in here in 2 milliliter solution? Well, before we add, we got 0.0100 mole. Will that caffeine go anywhere? No, that caffeine is still there. The mole still the same, right? You can do calculation right here. So 5 molar, plug 5 in there, and then volume is 2 milliliters, so 2 over 1,000. So the unit have to be liter, all right? So do calculation, same number. Yeah. So moles never change, right? Before dilution, after dilution, in the syringe, mole never change. So we can set up the equation like this: mole initial mole and a final mole. Before dilution, after dilution, mole never change. And well, but moles equal to M and V, concentration times volume. So you obtain this relationship. You know that? So molarity, concentration before dilution, volume before dilution, and then concentration and volume after dilution. Just one equation. Now let's take a look. If you have 30 milliliter of 2.5 molar solution of magnesium bromide that you wish to dilute to until the concentration goes to 0.50 molar, to what volume must dilute the sample? How much water in milliliter you have to add? Okay, anyway. All right, so it's just two occasions. The before dilution, 2.5 molar concentrated, and we have that volume. After dilution, we dilute it down to 0.5 molar, asking for the final volume. Okay. All right. So we're looking for, we're trying to find the VF. So I'm going to move MF to the other side. So divide the MF on both sides, you should get this. Okay. And the rest just plug in, guys. It's super simple. MI is 2.50 molar. VI initial 30 milliliter. Here we go. MF is 0.50 molar. Right? Do the math right there. You should get V final 150 milliliter. Okay, so that's a V final. So you have to dilute from 30 milliliter to 150 milliliter. All right. Now the question, another question: how much water in milliliter you have to add? Do you add 150 milliliter? Oh no. You don't add 150 milliliter. If you add 150 milliliter water, you're gonna end up with 180 milliliter because you already have 30 milliliter in there. Right? If you don't get what I say, let's take a look. All right, before dilution, you already have 30 milliliter of solution in it. Now we have to dilute up to 150 milliliter. How much water you have to add to get to 150? Only 120, right? You don't add another 150 milliliter water. Otherwise, you're gonna end up with 180 milliliter volume. Okay. All right, and that's it. So I'm gonna skip that. You don't need that. Here we go. No, skip. Okay, all right. That's what you need to know for this lab. So are you ready to do lab now? Okay. The next video. So we got one more video. So Tyler comes in, and we're gonna talk about what we will be doing in the lab. All right, this is gonna be a fun time. Let's go to the next video.